The definition of a limit is quite involved, and it is very difficult to show directly from the definition that a particular sequence converges. One drawback of the definition is to even apply the definition, you need to have a candidate for the limit, and then you can use the definition to show that the particular sequence converges to that limit. However, the purpose of the definition is not exactly to use the definition directly to show that limits exist, but rather you prove useful theorems that allow us to manipulate sequences to show that particular sequences have limits and compute those limits also. So these are called limit laws. So let me first describe some algebraic limit laws. Limit laws, limits and algebraic operations. So the hypothesis is as follows. Let an and bn be sequences converging to A and B respectively. Okay, then you have the first limit law, the sequence an plus bn. That means I'm defining a new sequence Cn whose nth term is nothing but the sum of the sequences an and bn, the nth terms of the sequence an and bn. Then Cn converges to, as you can guess, a plus b. Okay, and the second limit law is for a fixed C in R, the sequence Can converges to Ca. So I'm no longer using an elaborate notation, I'm just denoting the sequence by an expression for its nth term. So the sequence Can converges to Ca. 3. A and Bn converges to AB. Okay, the product of the sequences converges to the product of the limit. Fourth point, if B is not 0, then for sufficiently large n, Bn is not 0 and the sequence An by Bn converges to A by B. Now here is where I am being a bit imprecise. Recall the limit definition. When we had discussed the limit definition way back in an earlier module, I had mentioned that many times the sequences will not be defined from the first term. They will be defined after some particular point, or sometimes even the index will be negative also. So here is a case where this An by Bn may not be defined for all n, but the assertion is that for suitably large n, Bn is not 0, so An by Bn makes sense and An by Bn converges to A by B. Excellent. Now let's proceed with the proof one by one. Proof. So the first part, I have to show that An plus Bn converges to A plus B. Let n1 comma n2 be the functions coming from the definition of An converging to A and Bn converging to B respectively. That means these functions n1 and n2 will tell you how far along the sequence you have to go to make mod An minus A and mod Bn minus B less than epsilon. Okay. Now observe, for the first part, observe that mod An plus Bn minus A minus B is less than mod An minus A plus mod Bn minus B. This is just an application of the triangle inequality, and as I remarked earlier, applications of basic inequalities will be done without specific mention as to which inequality I am using. Especially the triangle inequality and the reverse triangle inequality, I will not hesitate to use it at all. I will use it left and right without even mentioning what I am doing. Okay, so you have mod an plus bn minus a minus b is less than or equal to mod an minus a plus mod bn minus b. But if n is greater than max of n1 epsilon comma n2 epsilon, then each one of these terms will be less than epsilon, right? Because if n is greater than max of n1 epsilon, then it's certainly going to be greater than n1 of epsilon. Therefore, mod an minus a will be less than epsilon. Similarly, for the term mod bn minus b. So, if n is greater than max n1 epsilon comma n2 epsilon, then mod an plus bn minus a minus b will be less than 2 epsilon. Okay. So choosing the function n to be max of n epsilon comma n2 epsilon, we have shown an plus bn converges to a plus b. Note, I am implicitly also using this k epsilon principle that we talked about in an earlier module. Fine. So this proof was rather easy. We are just going to choose the capital N function to be max of n1 and n2. Now part 2 I am not even going to prove, because part 2 is a special case of part 3. So let me just directly jump to part 3. Okay. Now what do we have to show? We have to show that mod an bn minus ab can be made less than epsilon. Okay. Well, this is a standard trick we are going to do. The terms that we have control over are terms of the type mod an minus a and mod bn minus b. Unfortunately, they are missing. But we have become experts at this from high school training. In fact, our muscles for this particular thing has been greatly developed. By repeated use, what we do is add and subtract an appropriate term. So this is same as a and bn minus a and b plus a and b minus ab. Okay, I have just added and subtracted the term a and b from this, which is less than or equal to mod an into mod bn minus b plus mod b into mod an minus a. Right? Now this in turn is again less than or equal to mod an minus a plus a into mod bn minus b plus mod b into mod an minus a. I have just now added and subtracted a in the very first term. Okay. Now this is again less than or equal to mod an minus a into bn minus b, okay, plus mod a times mod bn minus b plus mod b times mod an minus a. Okay. Now again if n is greater than n of epsilon, where n comes from previous part, not from previous, comes from part 1, maximum of n1 comma n2. Okay, if n is greater than n epsilon, what do we have? This very first term is less than epsilon squared. This term is less than epsilon. This term is less than epsilon. So what we get is this whole thing is less than epsilon square plus mod a epsilon plus mod b epsilon. Okay, which is less than epsilon into mod a plus mod b plus 1. Here I am assuming I'm assuming epsilon is strictly less than 1, which I can just choose. If I can show that the quantity that I'm interested in, mod a n b n minus a b is less than epsilon, whenever epsilon is less than 1 for n sufficiently large, then by the discussions that we have had in quite detail earlier, I would get a global function n defined from R plus to the natural numbers that does the job in the definition of convergence. So I have got finally that mod a n b n minus a b is less than epsilon into mod a plus mod b plus 1. So again, by k epsilon principle, we have shown that the function capital N works in the definition of convergence. Right. So this concludes the proof of third part, and second part just follows immediately from the proof of this part, because the sequence an is just the constant sequence C. Now for the final part, we have to first show that, or just Bn is not 0 if n is sufficiently large. Now choose epsilon to be defined to be mod b by 2. Okay, then we know that mod bn minus b is less than mod b by 2 for suitably large n, right? Okay, then which means mod b minus bn is greater than mod b by 2, is less than mod b by 2. Mod b minus mod bn is less than mod b by 2. Figure out which inequality from lectures earlier I am using. Now this shows that mod bn is greater than mod b by 2 for sufficiently large n. In fact, we know what this n is going to be. This is just n greater than n of mod b by 2, not n of n2 of mod b by 2. This will work. Okay, so that means that mod bn is not 0 for sufficiently large n, simply because mod b is not 0. Now once we have done this, we are going to show that mod an by bn minus a by b, it can be made less than epsilon. But instead of doing that, what I will do is we will show 1 by bn converges to 1 by b. Okay, if I can do this, then I can apply part 3 to conclude that an by bn converges to a by b. So how will I show that 1 by bn converges to 1 by b? Well, it's just brute force. I look at 1 by bn minus 1 by b, and this is, as we know, it's just mod b minus bn by mod b bn. Okay, now again, if small n is greater than n of epsilon, now epsilon is no longer what we define, mod b by 2 or whatever. Epsilon is now any quantity, really doesn't matter, in R plus. Then what we get is mod b minus bn will be less than epsilon. So whereas the denominator mod bnb, just one moment, let me make one slight change. What I will do is, I will not consider the function capital N that we had done before. What we will do is, we will be slightly more clever. Okay, choose the new function capital N, choose the function capital N. Remember, the capital N that was there earlier involve the sequence an also. So I shouldn't reuse that right now because it makes no sense, because what I'm trying to prove has no involvement of an at all. So that was a slight goof up, sorry about that. Well, choose capital N of epsilon to be max of n2 of epsilon comma n2 of mod b by 2. You will understand in a moment why I am doing this. Okay. Now what will happen? What will happen to the numerator if n is greater than epsilon? If n is greater than n of epsilon, then the numerator mod b minus bn, this is certainly going to be less than epsilon, right? Okay. Whereas the denominator is going to be mod bn is certainly going to be greater than mod b by 2, right? Not mod, sorry about that. 1 by mod bn, 1 by mod bn will be less than 2 by mod b. Why is this the case? Well, because by our choice of capital N of epsilon being max of n2 epsilon comma n2 of mod b by 2, we have already seen that mod bn will have to be greater than mod b by 2, right? If mod bn is greater than b by 2, 1 by mod bn has to be less than 2 by mod b, which means this whole quantity will be less than 2 epsilon by mod b square. Okay, I hope you followed this. This is slightly tricky, but it's not that difficult. You have shown that 1 by bn minus 1 by b absolute value is less than 2 epsilon by mod b squared. So again, by k epsilon principle, we are done. Okay. So this concludes the various algebraic properties of that limits enjoy. Always use these algebraic properties to conclude that limits exist. We will see several examples soon enough. Don't try to use the definition except as a last resort. Okay, now let me end with some more basic properties of limits. These have got to do with limits and order. Limits and order. Okay, let again an converge to a, bn converge to b, and suppose for all n you have an is less than or equal to bn. Okay, then a is less than or equal to b. Okay, now the proof of this is rather easy. Consider the sequence Cn defined to be Bn minus An. Then for all n, Cn is greater than or equal to 0. Okay, and Cn converges to C, which is going to be by definition B minus A. Why is that? Because the sequence minus An has to converge to minus A, and the sequence Bn plus minus An has to converge to B minus A, right? Now suppose C is less than 0. Okay, we will arrive at a contradiction. Then mod C minus Cn is equal to mod C plus mod Cn. Why is this the case? Well, observe that modulus C is less than 0. Observe that C is less than 0 and Cn is greater than 0, right? So, how did I get from this that modulus of C minus Cn is actually mod C plus mod Cn? Well, because C is negative and minus Cn is also negative. So, this quantity I could have written it as minus 1 into Cn minus C, the whole thing modulus, which is same as mod Cn minus C. I'm just reversing the thing. I'm just reversing the thing in an extremely unnecessarily complicated way. And Cn is now Cn is a positive quantity and minus C is also a positive quantity. So the modulus of this is just mod C plus mod Cn. Just from the definition of uh, modulus or absolute value. Okay. That means if I choose epsilon to be mod C, then mod Cn minus C is always greater than epsilon, right? Because mod Cn is or rather it will be greater than or equal to. Mod Cn minus C will always be greater than or equal to epsilon. This means Cn converging to C is impossible. So this contradiction finishes the proof. Okay. So one last theorem involving limits and order. This is called the squeezing theorem. Squeezing or sandwich theorem. I don't know the exact spelling of sandwich, so I apologize in advance. Let An, Bn, Cn be sequences such that An and Bn both converge to the same quantity A. Suppose Cn is squeezed in between An. An is less than or equal to Cn is less than or equal to Bn for all n and n. Then as you can guess, Cn also converges to A. Okay. Again, the proof of this is fairly straightforward. Observe that An minus A is less than or equal to Cn minus A is less than or equal to Bn minus A. Okay. All I have done is I have taken the inequality An less than or equal to Cn less than or equal to Bn and subtracted A from all the sides. Okay. Now fix epsilon greater than 0 for sufficiently large n, we simultaneously can guarantee that An minus A is less than minus epsilon and Bn minus B is less than epsilon. Why? I want you to think about why we can do this. Okay. So that means we have minus epsilon less than or equal to Cn minus A less than or equal to epsilon. Okay. In fact, you will have strict inequalities, but sometimes just for convenience, I will not keep track of whether something is less than or equal to. Any statement where I replace a less than by less than or equal to is still true, though not optimal. Okay, that's not really relevant to the proof. So that means mod Cn minus A is less than epsilon for sufficiently large n. Okay, this shows that Cn converges to A as required. So this concludes this proof. This is a course on real analysis, and you have just watched the module entitled Limit Laws.